Well, good afternoon. My name is Clayder Gonzalez. I'm from Peru, but I studied my master's at the Universidad de Chile. And there I'm going to present you the topic of part of my master thesis, which is the title is an improved feature extractor for the LiDAR odometry and mapping algorithm. Well. Maybe you don't. It's not in the world of robotics, the LiDAR odometry and mapping, which it's also known as LOM algorithm, is known for solving the SLAM problem, which stands for simultaneous localization and mapping. Mainly, this algorithm generates a map and estimates its position. The algorithm is responsible for generating a map. This algorithm, LOM, is the highest ranked algorithm in a famous dataset, well, kind of famous. I don't know if everyone is familiar with that dataset, which name is the KITTI benchmark, Vision Odometry benchmark. As I told you, is the highest ranked. So the colored points are the current scan, and the gray points are the generated map. So this algorithm is responsible for presenting a solution for this problem. I'm going to start with a short introduction, and I'm going to show you what I have done with experiments, the results, and finally the conclusions. Mainly, as I told you, the LOM algorithm is the highest ranked algorithm in the KITTI dataset, and it has one part. It has many parts. It's divided in many tasks. One of them is the feature extraction part, and that's the part that I have modified and in which I have made my contribution. When I started to study, this paper, which is the LOM algorithm, I started to study the different equations of this algorithm. It has some, I'm not going to describe any equation, but I just want to show you a general view of the equations. There are some equations for the mapping, for the odometry. There are other equations for the feature point correspondence. What called my attention was the feature extraction part. The feature extraction part of this LOM algorithm was that, for me, it was a short equation, and that called my attention because there were these elaborated equation in the other parts, and the feature structure was not a very elaborated equation. This equation, is responsible for classifying points as smooth and not smooth points. So this is an example of the LiDAR odometry mapping using the LOM features. The gray cubes are the features that the original LOM algorithm are extracting in the LiDAR scan. And one thing I noticed about these features is that they were not very stable, and they were not being repeated on each 3D complete scan. And when I was studying this algorithm, I was wondering if this can affect the whole algorithm. So there, for example, the algorithm is estimating the map, and in one part, the here, for example, in this part, the robot is stopped at a certain part of the map. This dataset was taken with the Velodyne VLP16 LiDAR, and here the estimated map started to rotate and didn't match the gray points. I mean, the colored points didn't match the gray points. So I noticed here an error with the Velodyne data using the original LOM algorithm. Because of this, I decided to change the feature structure. I studied several feature structures in the literature. I'm going to show you now just a short part of my results. One of these parts are I changed the original feature structure with the curvature scale space feature structure. I used, to do the experiments, I used this equipment. First, I use this equipment with this hardware devices in the simulation software Gazebo. I use this robotic platform, Husky A200, a Velodyne LiDAR, and a GPS. As I told you, I replaced the original feature structure with the CSS, which stands for curvature scale space algorithm. Since I was using the simulation software Gazebo, I started to play with the standard deviation range noise. Standard deviation of the sensor. So I started to going from some small values to some bigger values of standard deviation. An important finding happened, An important finding happened when I used a sensor range noise equal to 0.02 meters in the LiDAR sensor. As you can see here in the picture on the left is the original LOM algorithm. That is the estimated trajectory of the robot in the previous, which can be seen in the previous slide. So the estimated trajectory, as you can see on the picture on the left and on the green circles, are forming kind of peaks on the. It's not as smooth as the picture on the right, which is the modified version of the algorithm. So that made me conclude that the high sensor range noise was negatively affecting the original LOM algorithm. Maybe this wasn't noticed by the original author because they use a Velodyne LiDAR, which is a high precision LiDAR, but there are other LiDARs, maybe more affordable in cost, that has bigger values in the noise. They are not accurate many times. So I decided to test. To use this metric, which is known in the robotics community, which is called absolute trajectory error, and the error on the picture on the left show the errors on the X Euclidean component and Y Euclidean component of the original LOM feature structure, and on the right of my modified version with the CSS algorithm. This is just, I just wanted to show you some of my results. I have carried out more experiments, and you can find them my code is uploaded on my GitHub website. Finally, I'm going to show you what happened with the previous video. This is the video I showed you at the beginning, And this video was showing the loam algorithm, and it produced the rotation error. When I replace it with the CSS feature extractor, you can see there that the rotation error is not present anymore, at least in this data I have used. Thanks.